So in the last video, we summarized meiosis, and we said basically in humans, we start out with the parent cell of what's going to either be an egg or a sperm, a gamete of some sort. The initial cell has 46 chromosomes, but they all double in number, and when they double, we now call them chromatids. So we end up with 92 chromatids in this cell. This cell is going to divide during meiosis part 1, which is basically the first section of PMAT, the first phase of prophase, metaphase, anaphase, and telophase. After this first division, the cell now divides to 2, and each of these cells now have 46 chromatids. And then we're going to get a second phase of meiosis, or meiosis 2, and during this we have another round of prophase, metaphase, anaphase, and telophase, and what we end up with is 4 brand new daughter cells that are all different from one another. Each of these are going to end up with 23 chromosomes total, because if one of these eggs meets up with a sperm that also has 23, they're going to come together and form a diploid zygote with 46. Just like none of us are perfect, even though biology is so amazing and so awesome, it is not always perfect. It's sometimes mistakes happen. And I always have to tell you about these mistakes because a lot of you want to go into medicine, or maybe even you might see something like this in your real life. I hope you don't, but it's good to know about all these possibilities, right? So what could happen if there is a mistake during meiosis? So again, for example, our initial cell here is going to have 92 chromatids. And we said in a normal world, these will divide and the 2 new cells will have 46. But what happens if there's a mistake in meiosis 1, meaning the chromosomes weren't separated evenly? Then one of these new cells would have 48 chromatids instead of 46. The other one would have 44 instead of 46. So this one would have 2 extra. This one would have 2 less. Now normally, again in our normal situation, these 2 would split further and each new sperm or egg cell would have 23 chromosomes, which is what you need to produce a normal diploid cell. But what would happen in this case down here is there'd be an abnormal number in the end. 44 divided by 2 is 22. So these 2 cells would only have 22 chromosomes instead of 23. On the other hand, 48 divided by 2 is 24. So these 2 cells would have 24 chromosomes. If this egg was fertilized by a sperm, a normal sperm with 23 chromosomes in it, then that would mean these 2 eggs and this sperm together would produce a zygote with only 45 chromosomes. That would mean this child's, each one of their cells only has 45 chromosomes instead of the full 46. On the other hand, if this sperm mated with one of these 2 eggs, then the zygote would have 47 chromosomes. 23 plus 24 is 47. So this one would have an extra chromosome. Instead of the normal 46, it would have 47 chromosomes, an extra one. So this is possible scenarios of what could happen if there's a mistake in meiosis 1 in the first division. Now let's look at a different scenario. Let's say this time there's a mistake in meiosis 2. So meiosis 1 carries out like normal. These 2 are going to have 46. But let's say now the mistake happens in this second division. So this time, again, we're going to end up with 4 daughter cells. But let's say this parent cell divides improperly. One of the cells gets 24 chromosomes, the other gets 22. But let's say this bottom one doesn't have a problem. It divides like normal, and each one of these gets 23. And then we had a sperm here with normal 23. If this sperm came in contact with these 4 eggs, there's a 2 out of 4 chance there'll be a normal, healthy zygote, because there's 2 of these egg cells are normal. So if this sperm fertilized either of these eggs, it would be a normal zygote with 46 chromosomes. If somehow this sperm fertilized this egg, though, it would be abnormal. The zygote would only have 45 chromosomes instead of 46. Similarly, if the sperm fertilized this egg, there would be an extra chromosome. There'd be 47 instead of 46. And this sperm can only fertilize 1 egg at a time, so it's like a 50-50 chance that this zygote could either be normal or have an abnormal number of chromosomes. Now we have terms for all of these possible scenarios. The first term you should know is nondisjunction. Nondisjunction means there's an abnormal number of chromosomes. So for humans, that means there's not 46. It's not 46. If there's more or less than 46, it's a nondisjunction. And again, the way that this would occur is if there is a mistake during meiosis, like the scenarios we just talked about. If there's one too few chromosomes, it's a monosomy. So monosomy would be one too few chromosomes. In the case of humans, it would mean there was 45 total chromosomes instead of 46. On the other hand, a trisomy means there's an extra chromosome. So again, in the case of humans, it would be 47 instead of 46. If the cells had 47 individual chromosomes, that's an extra one. So these are the terms for when there is an abnormal number of chromosomes in the cell. Most of the time, if this happens, the zygote will not be able to survive. Like the embryo would not make it. If there's something this wrong, the baby will not make it to birth because it's just not normal. It's a defect and it cannot develop properly. But there are a few exceptions of cases where, when there is an extra or too few chromosomes, the baby is born. And typically, it leads to some secondary defect. I'll give you an example. If you look at this karyotype, at first glance, it looks like the ones we've seen before. But if you look at it closer, look at how chromosome set 21, instead of just 2, there's 3 here. So this would be what we call a trisomy 21, meaning there's an extra chromosome at set 21. And another name for this disease is Down syndrome. And I'm sure you've seen this before, right? Trisomy 21 Down syndrome. It leads to some secondary effects, such as maybe short stature, some mental disabilities. Okay, so just because of this extra chromosome, it can lead to other characteristics. Now, non-disjunctions can happen in either the egg or the sperm. It's possible that it can happen in either one, but it just so happens the majority of non-disjunctions are due to the egg. So what I mean by that, if it was a trisomy, it's usually the egg that had the extra chromosome 24, while the sperm had the normal number 23. It's more often than not from the egg. And here's the reason for that. For sperm, when sperm cells are produced, it's called spermatogenesis. So spermatogenesis is basically the meiosis or the replication of sperm cells. This happens in the testes. Now, sperm cell production doesn't happen until puberty. So this process occurs at puberty for biological males. So once puberty begins, this spermatogenesis process is happening all the time. And it's just going through PMAT1, PMAT2, and sperm are being constantly produced throughout the entire life. Okay, so until death. Between puberty and death, biological males can produce sperm at any point. Now it's quite different for egg cells. The production of egg cells is called oogenesis. This process occurs in the ovary. So for biological females, oogenesis occurs while they are still a fetus, so before birth. As a fetus, all the egg cells the individual will ever have are already produced. And on average, the number is around 40,000 egg cells, which really is not a lot to begin with. Now, at this stage, while still a fetus, these egg cells get paused in prophase 1. So at birth, all the egg cells are paused in prophase 1. Once this individual hits puberty, some of these egg cells each month will leave prophase 1 and they'll go all the way to metaphase 2. So each month, only a select number of these egg cells will leave, become undormant again, and make their way all the way to metaphase 2. If the cell is fertilized by sperm, it'll proceed all the way to the end of meiosis 2. So only if the egg is fertilized will it complete meiosis and we get a zygote. Now here's the problem. Between the time the individual's born and the time the egg is fertilized, it could be, 30 years. This is a long time for mistakes to happen in this egg cell. As the biological mother ages, there's a greater risk of non-disjunction occurring in the egg cells because they're getting older. This is just an example of the incidence rate of Down syndrome in females that have children at increasing ages. So for example, at 30 years of age, there's a 1 in 900 chance of the non-disjunction occurring. By the time this individual reaches 40, it's a 1 in 100 chance of Down syndrome occurring. And of course, if somebody were to give birth at nearly 50 years old, it's a 10% chance. And again, the reason why the egg is typically responsible for this non-disjunction is because they're all already made at birth. Whereas for the sperm, they're constantly being made, so there's less likely of a mistake occurring. There's a few other trisomies that are in autosomes, meaning in any of the sets between 1 and 22, other than Down syndrome, which is a trisomy 21. There's one called Patau syndrome, which is a trisomy 13. This affects about 1 in 5,000 live births. Many of the infants born with this syndrome never live past a few months. Those that do typically have severe cognitive defects, as well as perhaps vision issues and other facial issues. Edwards syndrome is another one that we see about 1 in 10,000 live births. This is a trisomy 18. The rate of survival is very low, and it does affect kidneys. That's where the main issue is kidney failure, as well as cognitive defects. Now remember I said that infants born with a non-disjunction in an autosome typically do not survive. It's much more common to see a non-disjunction in a sex chromosome. So let me show you what that would look like. Let's say we had this egg cell, which is XX, which means that all of the potential egg cells that get made after meiosis 1 will also have XX, and all of the possible new egg cells after meiosis 2, they're all going to have 1X. Whereas for sperm, which are XY, after meiosis 1, all of these cells are also XY. After meiosis 2, you have possible X here, possible Y here. And same thing here. This sperm cell could possibly have an X, and this one could possibly be carrying a Y. So anytime the X from the sperm meets with the egg, the individual will be XX. Any possible time that one of these Ys meets up with one of these X's, it'll be XY. So traditionally, you have a 50-50% chance of either having XX or XY. Just like I said before, that most non-disjunctions occur in the egg, it's still true for sex chromosomes. What possibly could happen is that instead of these X's separating, one of the egg cells accidentally gets an extra X, while the other gets nothing. And then for these two, they get normal splitting. So you can imagine one of a few different things happening. If this X was fertilized by another sperm that had an X, this could lead to an individual with, instead of 2 X's, they have 3. This is actually called trisomy X or triple X syndrome. And instead of 46 chromosomes, this is a trisomy, so this individual has 47 and they have 3 X's. Here's what the karyotype would look like. They have normal 1 through 22 autosomes, but 3 copies of X chromosome. Now, individuals with trisomy X tend to develop normally, and they even may have normal sexual development. They may just be a little bit taller than average, is what they are finding from statistics. So that's one possibility of what could happen if we had this non-disjunction occur in this cell over here. Now, another possibility that could happen is this Y could fertilize the cell that has the 2 X's, and what you end up with is XXY. So again, this would be a trisomy in the sex chromosomes. Now, individuals with XXY, this is actually a syndrome known as Klinefelter syndrome. This affects somewhere between 1 in 500 and 1 in 1,000 biological males that are born. Biologically, we would consider this male because there's still a Y chromosome there, but it could lead to some secondary effects. Individuals with Klinefelter syndrome tend to have no facial hair develop, very long legs. There will probably be some sexual development issues. So individuals with Klinefelters will likely never be able to have children of their own. Now there's one last possibility, is that this X fertilizes this egg that's missing a chromosome. So what you'll end up with is a zygote with one X but missing the second sex chromosome. So this would be a monosomy because this individual will have 45 chromosomes. They're missing one sex chromosome instead of 46. And this actually also has a name. It's called Turner syndrome. This affects about 1 in 2,500 biological females born. This is biologically considered female because there's no Y chromosome. So again, there could be some secondary effects due to this missing chromosome. Individuals with Turner syndrome, the main thing is that the ovaries may not develop properly and they may not be able to have children of their own as well. There are several other possible genetic disorders, but I just wanted to give you a few examples of ones that can occur when we have a non-disjunction during meiosis.